video will tell you about encryption algorithm that is called Camellia.
Introduction of Camellia encryption algorithm. This document specifies the convention for using the Camellia encryption algorithm. Camellia spec for encryption with the cryptographic message syntax (CMS). The relevant objective identifier OID and processing step are provided so that Camellia may be used in the CMS specification for contents and key encryption. This work was done when the first author worked for NTT. Camellia was jointly developed by Nippon Telegraph and Telephone Corporation and Mitsubishi Electric Corporation in 2000. Characterized by its suitability for both software and hardware implementation as well as its highest level of security. Camellia has been scrutinized by the wide cryptographic community during several projects for evaluating crypto algorithms.
Camellia was selected as a recommended cryptographic primitive by the New European Scheme for Signature Integrity and Encryption project. Terminology. The keywords of terminology: must not, required, should not, recommended, may, and optional. Object identifier for content and key encryption. Provide the OID and processing information necessary for Camellia to be used for content and key encryption in CMS. OID class define the content encryption algorithm and the others define the key encryption algorithm. CMS agent can apply Camellia either for content or key encryption by selecting the corresponding object identifier, supplying the required parameter and starting the program code. OID for content encryption. Include in the list of cryptographic techniques for Japanese e-government system which were selected by the Japan Cryptography Research and Evaluation Committee. Camellia is added to the set of symmetric content encryption algorithm defined in CMS ALG. The Camellia content encryption algorithm in cipher, block, chaining, CBS. OID for key encryption.
Hello everyone, today we will see about Camellia key wrap algorithm. What is key wrap? The key wrap algorithm are intended for applications such as protecting key while in untrusted storage or transmitting key over untrusted communication networks. Camellia key wrapping and unwrapping are done in conformance with the ASE key wrap algorithm because Camellia and ASE have the same bulk and key size. For Camellia key wrap, the input to the wrapping process are the KEK and the plaintext to be wrapped. The plaintext consists of N64-bit blocks containing the key data being wrapped. An alternative description of the key wrap algorithm involves indexing rather than shifting. This approach allows one to calculate the wrapper key in place, avoiding the rotation in the previous description. For Camellia Keep Unwrapped, the inputs to the unwrap process are the KEK and N164-bit blocks of ciphertext consistently of previously wrapped key. It returns N's block of plain text consistently of the N64-bit blocks of the decrypted key data. The unwrap algorithm can also be specified as an index-based operation, allowing the calculation to be carried out in place. Again, this produces the same result as the register shifting approach. Key data integrity, the initial value. In the final step of unwrapping process, the recovered value of AROK is compared to the expected value of AROK. If there is a match, the key is accepted as valid and the unwrapping algorithm returns it. If there is not a match, then the key is rejected and the unwrapping algorithm returns an error. For example, whether there is a need to determine the integrity of key data throughout its life cycle or just when it is unwrapped. This specification defines as default initial value that supports integrity of the key data during the period it is wrapped. Provision is also made to support alternative initial values. Default initial value. The default initial value is defined to be the hexadecimal. If unwrapping produces A0 or any other value, then the unwrap must return an error and not return any key data. Alternative initial values. When the key wrap is used as part of larger key management protocol or system, the desired scope for data integrity may be more than just the key data or the desired duration for more than just the period that is wrapped. Key wrapped implementation that are not application specific will require some flexibility in the way that the initial value is set and tested.
SMIME capabilities attribute.
What is the definition of SMIME?
SMIME is Secure Multipurpose Internet Mail Extension. SMIME is a standard for public key encryption and signing of MIME data.
Who developed SMIME?
It was originally developed by RSA Data Security Inc. and the original specification used the IETF MIME specification with the de facto industry standard PKCS7 secure message format. SMIME functionality is built into the majority of modern email software and interoperates between them. If an SMIME client is required to support symmetric encryption with Camellia, the capabilities attribute must contain the Camellia OID specified in the category of symmetric algorithms. The parameter associated with this OID must be Camellia SMIME capability. The SMIME capability sequence representing Camellia must be encoded as the following hexadecimal strings. When a sending agent creates an encrypted message, it has to decide which type of encryption algorithm to use. In general, the decision process involves information obtained from the capabilities list included in message received from the recipient, as well as other information such as private agreements, user preference, legal restrictions, and so on. If user require Camellia for symmetric encryption, it must be supported by the SMIME client on both the sending and receiving side, and it must be set in the user reference.
Okay, now let's move to security in Camellia. For your information, I was assigned to do the research about the Security consideration. So, here is my main discoveries. First, encryption-decryption process, differential and linear cryptanalysis, truncate differential cryptanalysis, truncate linear cryptanalysis, cryptanalysis with impossible differential, higher order differential attacks, and interpolation attack. Key scheduler, slide attack, relate key attack, not evaluate keys. Attacks on implementation, power analysis, timing attacks. Consider a modern safe chipper using the smaller key size option 128 bits. Consider inflexible to break, no non-successful attacks that weaken the chip considerably. So, for the conclusion, Camellia security is considered as one of the best in this field.
Intellectual property statement. The Cipher was developed in Japan by Mitsubishi and entity companies in 2000. It was later approved by the International Organization for Standards, the Europe Union's NESI project, and the Japanese Cryptrack project. Camellia generally collects personally identifiable information with your specific knowledge and consent. Camellia was designed to be efficient for both software and hardware implementations, and it is used in various devices from low-cost smart cards to high-speed network protocol. Mitsubishi Electric Corporation and Nippon Telegraph and Telephone Corporation have pending application of valid patents which are essential to Camellia. IETF takes no position regarding the validity or scope of any intellectual property or other rights that might be claimed to pertain to the implementation or use of the technology.
I will talk about citation of Camellia. Citation of Camellia. First, single key definition. Second, about related key, and the last one, other attacks. Single key definition. Both standard definition trains and trusted trains cover only around 1/2 of the total number of rounds. The attacker can pass a few more rounds. The security margin of Camellia is high. Hence, the cipher is resistant against attacks based on definition trains. Camellia applies standard cryptographic design techniques, and as there is no known analysis on such cipher showing a significant advantage of definition attack over the attack based on definition trains. A similar conclusion applies to the case of boomerang attack, as they are definition-based attacks. Next, our citation is related key differentials. Our analysis shows that finding the best related key trains is infeasible due to the relation in the ground key. Since we cannot give a precise bound on the related key trains. Related key definition, however, is applied only a modified version of Camellia and only in a hash function setting.
And the last one is other attacks. Camellia is resistant against slide attacks and rotation attacks, as this